If you've worked with vectors before, I urge you, please forget everything you think you know about them. Not because what you've learned is wrong, it probably isn't, but because I want you to understand why vectors have the properties that they do have. To understand that, we must approach vectors with a clear head, free from all preconceptions, free even from preconceptions that are true but poorly understood. There are various ways of introducing vectors and developing their properties, each with its own advantages and disadvantages. I like to introduce vectors geometrically. The advantage of this approach is that it makes vectors very tangible. The disadvantage is that when we begin geometrically, it takes a little more work to develop vectors' important algebraic properties. But I actually think that this supposed disadvantage turns out to be a big blessing in disguise because it forces us to dwell on some fundamental algebraic ideas in a geometric setting. You have probably never done anything like that before, since algebra is always introduced in school as something built on top of arithmetic. So in a strange way, it turns out that introducing vectors geometrically will help you appreciate algebra, and I hope see it in ways that you've never considered before. With these preliminaries out of the way, let's bring in some vectors. We'll begin by defining a vector to be a directed line segment, a little arrow, a geometric object with magnitude, the arrow's length, and direction, the direction in which the arrow points. I'll note in passing that vectors are used to represent so many things in physics precisely because there are so many things in physics that have magnitude and direction. Simple examples include forces, velocities, and displacements, all of which are represented by vectors. But enough of physics. We'll begin, and this is where some of you must purge your minds of preconceptions, by thinking of vectors as arrows and only as arrows. In particular, those of you who have met vectors elsewhere might be used to thinking of them as lists of numbers, and you might be used to relating vectors to coordinate axes. If so, please banish such ideas from your mind, at least for now. Vectors can live in two-dimensional space, or three-dimensional space, or even in spaces of 4 or more dimensions. But you are to think of such spaces as unspoiled, virgin territory, pure, organic, carbon-neutral, and, above all, coordinate-free. For ease of reference, we usually name the vectors that we work with. Typical vector names are v, w, a, b, c, etc. And to emphasize that these symbols stand for vectors, we put little arrows over their names. Vectors, as I've said before, are characterized by magnitude and direction. Nothing else matters. A very silly example of something that doesn't matter is a vector's color. Changing a vector's color doesn't change the vector, since its magnitude and direction stay the same. More substantially, another thing that doesn't matter about a vector is its position. We can translate a vector wherever we like, and the result is still the same vector so long as its magnitude and direction remain the same. Or to put it another way, all of these are the same vector, since they all have the same magnitude and direction. Similarly, these vectors are all equal. Okay, now that we know what vectors are, and we know what it means for vectors to be equal, we're ready to introduce vector addition, which should sound like a strange concept. We know what it means to add 2 numbers, of course. But can we somehow add geometric objects? It sure sounds peculiar, but this is exactly what we are proposing to do when we talk about adding vectors. So how do we do it? Given 2 vectors v and w, what do we mean by v plus w? I shall tell you. We start with vector v, translate vector w so that it starts at v's endpoint, and then we draw the vector that stretches from the beginning of this 2-stage path to its end. That vector is what we define to be v plus w. This process is sometimes summarized by saying that we add vectors tip to tail. This tip-to-tail addition works in all situations, regardless of whether the vectors lie in a 2-dimensional space, a 3-dimensional space, or a 42-dimensional space. For that matter, it works even if the vectors lie in 1 dimension along the same line. If the vectors point in the same direction, then adding tip-to-tail gives the obvious result. If the vectors point in opposite directions, adding tip-to-tail still works out nicely. Okay, now that we know how to add vectors, we can explore the algebraic properties of vector addition. We'll begin with a simple question. Is vector addition commutative? Some of you may now be thinking, hey, that's not a simple question. I don't even know what it means. If that's you, let me remind you about commutativity. Given any 2 vectors, a and b, we could form the vector sum a plus b, but we could also form the vector sum b plus a. The question is, are these 2 sums always equal to each other? If this is always the case, then we would say that vector addition is commutative. That's the meaning of the question, but the question remains, is vector addition commutative? We can answer this question just by following our noses. Suppose we have 2 vectors, a and b. First, let's use them to form a plus b in the usual way. Now we just have to form b plus a and see if we get the same thing. Since we're free to translate vectors, let's draw a copy of b starting at the tail of a. This was a strategic place to put it because when we add a to it, we complete this nice parallelogram, and of course we see at once that b plus a is indeed equal to a plus b. It's clear that this will always be the case, so we may conclude that vector addition is commutative, and we can celebrate by booting that question mark at the bottom of the screen off the equal sign. Good! We've now used simple geometry to establish our first algebraic result about vector addition. There were no coordinates involved, no numbers of any sort, and while digging for commutativity, we also unearthed something valuable that we weren't looking for, an alternative but equivalent way to add vectors. We'll see this better if we clear out some of the detritus here. Instead of adding vectors tip to tail, this figure shows us that we could also add them with a parallelogram. To do this, we just put the two vectors we want to add tail to tail, draw the parallelogram that they determine, and finally draw the diagonal emanating from the two tails. That diagonal is the vector sum. And because we know that vector addition is commutative, we're safe just saying the vector sum. We don't have to specify the order in which the two vectors are added. Okay, before moving on to another algebraic property, I would be remiss if I didn't issue a quick public service announcement. Not all operations are commutative. An obvious example of a non-commutative operation is ordinary subtraction. 7 minus 2 is 5, but 2 minus 7 is minus 5, which is not the same thing. Similarly, 2 to the power of 3 is not the same thing as 3 to the power of 2. You can surely think of other basic examples too. I mention this here to put you on guard, because before too long, we will meet a kind of non-commutative vector multiplication, so don't take commutativity for granted. Let's proceed to another important algebraic question about vector addition. Is vector addition associative? Hey, what does that mean? Let me remind you. Associativity is a subtle property that concerns regrouping. Given any three vectors, a, b, and c, we can form the sum a plus b plus c, but we could also form the sum a plus b plus c. Will these always be equal to one another? If so, then we say that vector addition is associative. If it's not associative, then it will be an awkward operation, since we'll have to be very careful with parentheses. So let's hope it is associative. Well, is it? Let's figure it out. Let's let a, b, and c be three vectors. From them, we'll form the expression on the left-hand side. We'll start by putting b at a's tip, which sets us up to construct a plus b. To this vector, we must still add c, so we put c's tail at its tip and obtain the vector sum in the usual way. The vector we've just produced is the expression on the left-hand side, a plus b plus c. Good. Now we must produce the expression on the right-hand side and see if we get the same thing. The right-hand expression begins with vector a. To it, we must add b plus c. And now it's easy to see that the result of this sum is indeed our old friend from the left-hand side. Thus, the left-hand side and right-hand side are indeed equal, and we can declare in triumph that vector addition is associative. Thank God. But again, I need to urge caution in the future, because not all operations are associative. Here too, ordinary subtraction is an example of a non-associative operation. 5 minus 2 minus 4 is equal to minus 1. But 5 minus 2 minus 4 is equal to 7, which is a very different result. Similarly, exponentiation is non-associative. But subtraction and exponentiation are sort of easy examples of non-associative operations, since after all they aren't even commutative. You might wonder if it's possible for a commutative operation to be non-associative. It is possible. My favorite example is the operation of deciding the winner in rock, paper, scissors, the game you no doubt played at some point in your childhood. This operation is clearly commutative. For example, given rock and scissors, the winner, as everyone knows, is rock, since the rock crushes the scissors. And of course, the order is immaterial. Given scissors and rock, the winner is still rock. So deciding the winner in rock, paper, scissors is commutative, but it is not associative. Behold, rock, paper, scissors reduces to paper, scissors, since as any child can tell you, paper covers rock. And the winner of this contest is scissors, since scissors cuts paper. However, if we had started with the same three elements in the same order, but with the grouping changed, we'd have rock, paper, scissors, which reduces to rock, scissors, which in turn reduces to rock. So changing the mere grouping changes the outcome of this operation, which is commutative but is not associative. Okay, vector addition is the first of the two fundamental vector operations. The second fundamental vector operation is known as scalar multiplication. This is a much simpler operation. If we start with a vector v and scale it up to twice its length, keeping its direction of course, then we call the new vector 2v. We can view this new vector as a kind of product of the original vector v and the number 2. In the context of such a product, we often call the number a scalar to reflect what it accomplishes geometrically. That's the basic idea of scalar multiplication. Of course, we need not scale by 2. If we were to scale v down to 31% of its original length, the new vector would be 0.31v. More interestingly, if we scale vector v by a factor of 1.4, but also reverse its direction, we say that we've scaled it by negative 1.4, so that the result is negative 1.4v. This convention gives us a nice algebraic way to represent a vector v's opposite, meaning the vector that points in the exact opposite direction as v, but with its same length. This vector is simply minus 1v, which we further abbreviate as minus v. For that matter, it's worth noting that vector v itself can be written as 1v, since stretching something by a factor of 1 doesn't change it at all. So just as in ordinary arithmetic, multiplication by 1 changes nothing. What about multiplication by 0? In ordinary arithmetic, multiplying any number by 0 turns any number into 0. Something similar happens here. Scaling any vector by 0 leads to a vector with 0 length, and thus with no real direction. Essentially, it becomes a point. You might think this result shouldn't count as a vector anymore, but it's useful to still call it a vector. In fact, we call it the 0 vector, and we symbolize it as a 0 with an arrow on top of it. Now, if we're going to accept the 0 vector as a genuine vector, we have to be able to add it to other vectors. How do we do that? Exactly as you'd expect. By definition, for all vectors w, w plus the 0 vector will be w itself. Good. Now let's develop the basic algebraic properties of scalar multiplication. We'll start with some simple observations. We're given this vector v. Suppose we scale it by a factor of 3. Now suppose we scale the resulting vector by a factor of 2. Clearly, the net result of these two operations is that the original vector has been scaled by a factor of 6. That is, scaling by 3 and then scaling the result by a factor of 2 is equivalent to scaling the original vector by 2 times 3 all at once. More generally, scaling any vector v by any scalar beta and then scaling the result by alpha is equivalent to scaling the original vector v by alpha times beta all at once. This is true regardless of whether the scalars are positive, negative, or 0, as you can easily verify for yourself. Okay, so we've just established an important associative property of scalar multiplication. Let's move on to a distributive property. If we start with any vector v, scale it by 3, and also scale it by 2, and then we add the scaled vectors, the result is obviously the original vector's direction, but stretched by a factor of 5. That is, adding 3v and 2v is equivalent to scaling v by 3 plus 2. More generally, scaling any vector by 2 scalars and adding the results is equivalent to scaling the original vector by the sum of the 2 scalars. Reading this equation from left to right, it tells us that we can distribute a vector v over scalar addition. So far, so reassuring. This still looks like ordinary algebra, but there's another sort of distribution we must also consider. Namely, is this statement true? Can we distribute a scalar over vector addition? Don't be fooled into thinking the answer is an obvious yes. Remember that person in pre-calculus who thought that everything distributes over addition, when in fact most things do not. That person didn't pass pre-calculus, so get those thoughts out of your head. So the question remains, can we distribute a scalar over vector addition? Let's see. The algebraic statement involves 2 vectors, v and w, as well as alpha v and alpha w. In fact, it concerns the sums of the vectors in each pair. Now look at these 2 triangles. Because the black vectors are parallel and the purple vectors are parallel too, we know that the angles between each pair must be equal. Aha! Now we know that the 2 triangles are similar by the side-angle-side similarity criterion. Since the triangles are similar, every side in the larger triangle is the same multiple of the corresponding side of the smaller triangle. This scaling factor is obviously alpha, so it must be the case that the green vector in the big triangle is alpha times the red vector of the small triangle. Ah, but look what we've just established. This is the very statement we wished to prove, so we can get rid of that question mark. We've now proved that this form of distribution holds too. Okay, a few words on vector subtraction are in order. We'll look at subtraction in two ways. For our first view, we'll note that in a fundamental sense, we already know how to subtract vectors, since vector subtraction is just the addition of a negated vector. Symbolically, v minus w can always be replaced by v plus negative w, which we already know how to handle geometrically. That was easy enough, but there's a second geometric view of vector subtraction, equivalent to the first, that's well worth bearing in mind. It's easiest to understand this second view by thinking about the algebraic expression v minus w. Whatever v minus w is, it has the algebraic property that adding it to w gives us v. This algebraic characterization of v minus w as the vector we must add to w to get v can be interpreted geometrically. If we put the tails of the vectors together, it's easy to see precisely which vector we must add to w to get v. We can summarize this second view as follows. When v and w emanate from the same point, like this, then the vector between their tips pointing to v, like this, and not the other way around, is v minus w. This geometric characterization of vector subtraction often comes in handy. And now, at long last, we are ready to talk about scaffolding, or rather, we are ready to talk about coordinates. We can introduce them as follows. Once we've laid down coordinate axes in the plane, we draw two unit-length vectors that extend from the origin along the positive axes. We give these unit vectors special names. The one along the x-axis is called I hat, and the one along the y-axis is called j hat. Those hats indicate their special status in this coordinate system. The first thing to observe here is that every vector in the plane can be understood as a weighted sum of I hat and j hat. Here, for example, it's clear that v can be viewed as 5 copies of I hat plus 3 copies of j hat. Or, if we look at another vector, w, we see that w is equal to I hat plus negative 2 copies of j hat. That is, w is I hat minus 2 j hat. This is easy enough, but why is it important? It's important because it gives us a way to add vectors algebraically. We already know how to add v and w geometrically. It's just the usual tip-to-tail trick. But now that we've written v and w as weighted sums of I hat and j hat, we can find v plus w simply by adding their weighted sum representations. Looking at this sum, we clearly end up with 6 copies of I hat and 1 of j hat. That is, v plus w is 6 I hat plus j hat, whose position in the plane we can easily locate. It's worth dwelling on this simple vector sum that we just did in our heads. We've carefully designed vectors so that we can do such sums more or less automatically, but we should, just this once, look under the hood to see what actually justifies our quick summation. We'll see that it all depends upon the various algebraic properties that we carefully proved from our geometric definitions of basic vector operations. So, let us commence the dark arts of careful justification. We're adding 5i plus 3j to I minus 2j. Is the sum really 6i plus j? Let's see if we can justify this entirely algebraically, using only statements that we've proved. We've proved several results about scalar multiplication and vector addition, so to put ourselves in a position in which we can use these results, we should begin by rewriting that one vector subtraction of 2j as the vector addition of minus 2j. Next, think of the stuff within the red parentheses as one block, so that we can think of this whole expression as the sum of 3 terms: the red block, I hat, and minus 2j hat. Thinking of it this way lets us invoke the associativity of vector addition. Shifting those yellow parentheses from the last 2 terms to the first 2 terms, we obtain this new expression. The strategy here is to try to bring the I hat terms together. To accomplish that, we'll first reassociate inside the yellow parentheses, and then we'll use the commutativity of vector addition to reorder the terms inside the red parentheses. Another application of the associative property shifts those red parentheses, and now we've brought 5i and I together. Of course, it's geometrically obvious that 5i plus I is 6i, but we're trying to do this without relying on geometric intuition at all, as though we were trying to get a machine to understand the algebra of vectors, and machines obviously can't be expected to have geometric intuition. Have we proved enough to allow our intuitionless machine to deduce that 5i plus I is 6i? Can we use the algebraic rules that we've proved to establish this? The answer is yes. Here's how. First, we can rewrite that I hat as 1 times I hat. Then we can factor I hat out of the red parentheses, which is allowed by one of the distributive properties that we've established. Now inside those red parentheses, we're just left with 5 plus 1, which we can happily agree is 6, since the statement that 5 plus 1 is 6 has nothing to do with vectors. We've run out of room, but this is easily fixed. Now we just need to bring the j hats together. The way to do that is similar to what we've done already. Reassociate, then factor j hat out of the parentheses. By ordinary arithmetic, this reduces to 6i hat plus 1j hat, which by definition is the same thing as 6i hat plus j hat itself. And we have answered our question. Yes, v plus w really is 6i hat plus j hat, as claimed. Of course, you do not have to do this sort of exhaustive and exhausting justification in practice, but you should do it once or twice for the good of your soul. It will help you appreciate the fundamental importance of properties such as associativity and commutativity that we use all the time more or less unthinkingly. Everything that we've said about vectors in the two-dimensional plane can be extended to vectors in three-dimensional space. In this context, we have 3 special vectors, the unit vectors in the positive x, y, and z directions. These distinguished vectors are known respectively as I hat, j hat, and k hat. Now if we take any vector v in space, we can always translate it to the origin, from which point we can see how to write it as a weighted sum of I hat, j hat, and k hat. The easiest way to visualize this is to drop a perpendicular from v's tip to the xy plane. From the foot of that perpendicular, drop further perpendiculars to the x and y axes. Now do the analogous thing with respect to the xz plane and with respect to the yz plane. Now we have a box in which our given vector v is a diagonal. By moving along the edges of this box, we obtain scalar multiples of I hat, j hat, and k hat. Adding these vectors tip to tail, we clearly obtain v. In the case depicted, for example, we find that v is 2.5 I hat plus 5 j hat plus 6 k hat. This is v's decomposition into a weighted sum of I, j, and k. Every vector in space has its own particular decomposition of this sort. For this reason, vectors in space are often presented algebraically in just such a form. For example, if we're told that w is 4i minus 2j plus 3k, we can read this weighted sum as a set of marching orders that lead us inexorably to the vector w. Now, if we wish to add v and w, we know what this means geometrically. But we also can carry out the addition algebraically by adding the corresponding terms in v and w. Doing so, we clearly end up with 6.5i plus 3j plus 9k. Now when you think about that vector sum that we just carried out, the notation looks more cumbersome than it really needs to be. Accordingly, we'll introduce some shorthand notation for vectors. The expression ai hat plus bj hat plus ck hat is often abbreviated in the following way. We just peel off the coefficients, separate them with commas, and enclose them in angle brackets. So for example, if we look at vector v, we can rewrite it simply as 2.5, 5, 6 in angle brackets. Similarly, we can rewrite w as 4 minus 2, 3, which I'll do now. With v and w written this way, it's even easier to add them. We just add the corresponding components. Naturally, this works in 2 dimensions too. We just have 2 components instead of 3. A vector such as minus 1, 3 can be interpreted as more concise marching orders. Moreover, this shorthand notation makes scalar multiplication as easy to carry out as vector addition. For example, if v is minus 1, 3, then we can easily obtain the coordinates of minus 2v simply by multiplying each coordinate of v by minus 2. Thus, if v is minus 1, 3, then minus 2v is 2 minus 6. It's worth mentioning that there are some alternate shorthand notations besides ABC in brackets. Some people just write ABC with ordinary parentheses instead of angle brackets. I don't like this because it's often useful to distinguish visually between the point ABC and the vector ABC. A more common shorthand, especially in linear algebra, is to write the coordinates vertically. This makes sense for reasons having to do with matrices, which are rife throughout linear algebra, but outside of that context, the angle bracket convention is usually the clearest. There's one last topic to discuss before we end this introduction to vectors. We need to discuss how to compute the length of a vector given its coordinates. This turns out to be quite simple. Suppose we have a vector v in the plane with coordinates a, b. How long is that vector? We can answer this by translating the vector to the origin and dropping a perpendicular to the x-axis to form a right triangle. In this particular picture, the length of the horizontal leg is, of course, a, but we must be a little careful about the vertical leg. Its length can't be b, because b clearly represents some negative number, and lengths can't be negative. We can, however, say that the vertical leg's length is the absolute value of b. In fact, while we're at it, let's say that the horizontal leg's length is the absolute value of a. By doing this, the argument we're making will hold no matter which quadrant v lies in. Well, now we have a right triangle whose legs are known, so Pythagoras tells us what the hypotenuse's length must be. Notice that we can simplify this expression. Squaring a number's absolute value is the same as squaring the number itself, so we can just get rid of those absolute value signs under the radical. And we can now draw our conclusion. If vector v is ab, then its length is the square root of the sum of its squared coordinates. There's also a symbol we use to denote a vector's length. The length of v is denoted this way, 2 vertical bars on either side of the vector. Using that notation, we can write that v's length is the expression we found a moment ago. Naturally, we'd like to carry out the same analysis next in 3 dimensions. Given any vector v in space, with coordinates a, b, c, what is this vector's length? We can find the answer as we did in the earlier case. Once we've translated back to the origin, we drop the expected perpendiculars. The length we seek is now a body diagonal of this box, whose edges are the absolute values of the vector's coordinates. Drawing a diagonal of the box's bottom face, we obtain a right triangle in the bottom face, whose hypotenuse must be the square root of a squared plus b squared by the Pythagorean theorem. This hypotenuse, however, is the leg of another right triangle, whose other leg is the absolute value of c. Consequently, the hypotenuse of that triangle must be the square root of a squared plus b squared plus c squared. And this is in fact the length that we're seeking. Thus, using the customary symbols, we can say that the length of v is, once again, the square root of the sum of its squared coordinates. For example, if v is 2 minus 5, 3, what is the length of v? We solve this just by following the recipe we've derived. The length of v is the square root of the sum of its squared coordinates, which turns out to be the square root of 38. And that, my friends, is the end of the lecture.